Hello, my name is Juan Valencia and I will be discussing the 9-point circle and its applications. We will be using various lemmas to prove the 9-point circle theorem. The first one is that the perpendicular bisectors of a triangle's sides are concurrent at the center of the circumcircle. As you can see here, all of the perpendicular bisectors converge on one point R, which is the center of the circumcircle. The second lemma is if a triangle ABC is a right triangle and line segment AB is the hypotenuse of the triangle and the diameter of the circle, then point C lies on the circle, hence the circle circumscribes triangle ABC. The third lemma is that all triangles are cyclic. By using lemma 2, we can create a rectangle and go across the diagonal to create the circumscribing circle of the rectangle. The fourth lemma is that the line segment from the midpoints of two sides of a triangle is parallel to the third side and is half the length of the third side. As you can see in the picture, line DE is half the length of line AB. The fifth lemma is that the altitudes of a triangle intersect at a single point of concurrency called the orthocenter. As you can see here, the altitudes of the triangle intersect at the point H. Lemma 6 is the central angle is double the measure of the inscribed angle. As you can see here, the angle that is the central angle is always double that of the inscribed angle. Lemma 7 states that for a triangle ABC, the radius of the circumcircle is the multiplication of the length of all of the sides of the triangle divided by 4 times the area of the triangle. Now, with these lemmas, we can prove the theorem of the 9-point circle. The 9-point circle theorem states that in any triangle ABC, the feet of the altitudes, the midpoints of its sides, and the midpoints of the points between the orthocenter and the vertices are all concyclic on the same circle known as the 9-point circle, and its radius is half the radius of the circumcircle. To prove the 9-point circle theorem, we start with the midpoints of the triangle, the feet of the altitudes of the triangle, and the midpoints between the orthocenter and the vertices. Then by using lemma 4, we can make a triangle ACH, and notice that the midpoints of the sides are PA, MB, and PC. So we can take PA and PC to be parallel to the side AC. Then since MA and MC are also midpoints of the triangle ABC, then MAMC is parallel to AC. So the line MAMC is parallel to the line PAPC. Then we can take the triangle BCH, and the midpoints of the sides will be MA and PC and PB. And we can take MAPC to be parallel to HB. Similarly, we can take in the triangle ABH, the midpoints MC and PA, the line MC, PA is parallel to BH. So the line MC, PA is parallel to MA, PC. Then notice that the lines MC, PA, and MA, PC are perpendicular to the side AC since they are parallel to the line BNB, which is an altitude of the triangle. Hence the line MAPC is perpendicular to the line PAPC. and it is also perpendicular to MAMC. The same follows for the line PAMC is perpendicular to MAMC and PAPC. So the figure created by the points MA, PC, PA, and MC is a rectangle. By lemma 3, all rectangles are cyclic, so we can draw a circle around those points. Similarly, we can make another rectangle using the other midpoints, MB, MC, for the triangle ACH, and that will be parallel to the side ANA. Then we can take the midpoint MC, PB for the triangle ABH, and the line MC, PB will be parallel to the line ANA. So the line that goes from MC to PB is parallel to the line MB, PC. Therefore, PB and MB also lie on the same circle. Then we can take one of the rectangles, choose MA, PC, PA, MC, and notice that a diagonal will form a right triangle at MC, PC, NC, and by lemma 2, NC will lie on the circle. The same can be done for the points NB and NA. Thus, MA, PB, MC, NC, PA, MB, NB, PC, and NA all lie on the same circle, called the 9-point circle. Now take the rectangle MA, MC, PA, PC, and draw the diagonals of the rectangle. The intersection of the diagonals is the center of the 9-point circle. Now we can use lemma 1 to show that the intersection of the perpendicular bisectors will all intersect at R, and by lemma 7 we can show that the radius of the circumcircle of the triangle ABC. By lemma 7, the radius of the circumcircle of triangle ABC is the length of the side AB times the length of the side BC times the length of the side AC, divided by 4 times the area of triangle ABC. Now let's use the medial triangle formed by MA, MB, and MC, and notice that MA, MB is equal to AB over 2. So it follows that MA, MC is equal to 1/2 of AC, and MB, MC is equal to 1/2 of BC. Further, notice that the area of the medial triangle is equal to 1/4 of the area of the triangle ABC, since the sides of the triangle are 1/2 the size of the triangle ABC. Then using lemma 7 again, we can show that the radius of the 9-point circle is equal to the side MAMB times the length of the side MAMC times the length of the side MBMC, divided by 4 times the area of the medial triangle MAMBMC, which we said was 1/4 of the area of triangle ABC. Then we can substitute the sides MAMB to equal to AB over 2, and MAMC to equal AC over 2, and MBMC to equal to BC over 2, to give us that AB times BC times CA divided by 8 over the area of triangle ABC, which is equal to 1/2 the radius of the circumcircle. Hence, the radius of the 9-point circle is half the radius of the circumcircle. Lemma 8 states that any triangle with orthocenter H, the line segment AH equals 2 times R times cosine of angle A, where R is the radius of the circumcircle. This lemma can be used to compare the length of sides, and this will be useful to be able to compare the 9-point circle and the circumcircle. For the first application, we will introduce a proposition. The center of the 9-point circle is the midpoint of HR. In particular, the center of the 9-point circle is on the Euler line, the line that goes through the orthocenter and the circumcenter. Using lemma 8, we can show that the length of PAH is equal to R cosine of angle A, since PAH is equal to 1/2 of AH. Then we can take the right triangle RMA and B, and by lemma 8 again, the side RMA is equal to R cosine of angle R. Since triangle RBC is an isosceles triangle, by lemma 6, angle A in triangle ABC is equal to angle R in triangle RMAB. Thus, PAH is equal to RMA. Then notice that PAH is on the altitude of the triangle ABC, which is parallel to the perpendicular bisector of the triangle. Thus, RMA and PAH are parallel to each other. So MA, H, PA, and R are a parallelogram. Then notice that MAPA is a diagonal that is also a diameter of the 9-point circle, with O at the center. Hence, O is also the midpoint of the line HR. So O lies on the Euler line. The next application of the 9-point circle will be proposition B. The tangents to the 9-point circle at the midpoints form a triangle that is similar to the orthic triangle formed by the 3 legs of the triangle. The orthic triangle will be NA, NB, and C. From lemma 8, we can see that H, PA, R, and MA is a parallelogram. Similarly, since APA is equal to PAH, we can take A, R, and PA, MA to also be a parallelogram, since APA is equal to RMA and APA is parallel to RMA. Thus, AR is equal to PAMA. Note that chords in a circle are perpendicular to diameters in a circle. So NB, NC is perpendicular to MAPA. Then since AR is parallel to MAPA, you get that AR is perpendicular to NB, NC, and CR is perpendicular to NA, NB, since AR, BR, and CR are radii of the circumcircle. Then the tangents of the 9-point circle at the midpoints of ABC will be orthogonal to AR, BR, and CR. Thus, NA and B will be parallel to the tangent of MC, and NA-NC is going to be parallel to the tangent at MB, and NB-NC is going to be parallel to the tangent at MA. Hence, the 3 tangents form a triangle similar to the orthic triangle. The next application is proposition C. The 9-point circle is tangent to the inscribed circle of the triangle. So here we have I as the center of the incircle and O as the center of the 9-point circle. We have the 3 points J, K, and L, which are the points that are tangent to the sides of the triangle. And we have the points MA, MB, and MC, which are the midpoints of the triangle. Note that the line segment IJ is perpendicular to BC, and similarly IK is perpendicular to AB, and IL is perpendicular to AC. Next, what we want to do is reflect the tangent points across the angle bisectors of the triangle to get the points J prime, K prime, and L prime. And notice that they also lie on the incircle. Then notice that the line segment IJ prime is parallel to OMA. And similarly, IK prime is parallel to OMC, and OMB is parallel to IL prime. Then if you create a line that passes through the points, the midpoints, and then the reflected points, as in MA, J prime, and a line that passes through MC, K prime, and a line that passes through MB, L prime, those three lines are concurrent on one point that is tangent. Those points are concurrent on a point that lies on the 9-point circle and on the incircle. Hence, the 9-point circle is tangent to the inscribed circle of the triangle ABC. For the last proposition, we will need a corollary. The 9-point circle is the circle with the center at the midpoint of the orthocenter and the circumcenter with radius r/2. Proposition D states, all triangles inscribed in a circle that have the same orthocenter have a common 9-point circle. As you can see in the image, if you take triangles that are inside of the 9-point circle, you can see that they all have a 9-point circle that is similar. In fact, since all of the circles are from triangles that have the same circumcircle, they're all the same size. Hence, by corollary 1, the 9-point circles of the medial triangle, the orthic triangle, and the triangle created by the midpoints of the orthocenter and the vertices will have a radius that is r/4, so they all have the same radius. Since the radius of the 9-point circle of the triangle ABC is equal to r/2. This concludes the proofs and applications of the 9-point circle. Thank you for your time.